Hello and welcome to the third episode of Chicago Dialogues, a program that features a faculty member of the University of Chicago in conversation with an eminent personality from the Indian subcontinent. The program is produced by the University of Chicago Center in Delhi in collaboration with Prohor.in. I am Dipesh Chakravarti. I teach history and South Asian studies at the University of Chicago and am currently the faculty director of the Delhi Center. Today's conversation focuses on the work of Professor Sidney Nagel, my colleague in the physics department, and engaging him in conversation will be Professor Sabyasachi Bhattacharya, an eminent Indian physicist. Our usual anchor, our friend and writer Abhik Chanda, is working backstage today. I will introduce our guests, and Professor Bhattacharya will act as both the anchor of and a participant in this evening's program. Professor Sidney Nagel is the Stein-Freiler Distinguished Service Professor in our Department of Physics. He is a much decorated physicist with many awards and much recognition coming his way. Just to mention a few recent ones, he was awarded the Oliver F. Buckley Condensed Matter Prize in 1999 and was elected to the National Academy of Sciences in 2003 and to the American Philosophical Society this year in 2020. Nagel's work focuses on such things as drawing attention to phenomena like the science of drops, granular materials, and jamming. He's also interested in understanding the properties of disordered materials. As his website puts it, a perfect crystal of a chemical element or a compound is composed of an ordered arrangement of atoms. But in a disordered system, a glass for example, the atoms are in disarray. Disordered systems also exist on a larger scale, as with sand grains in a sand pile. As you will see, his work includes high-speed photography of splashing liquids and drop formation for his studies wonderfully amazing everyday things like the pesky rings deposited by spilled coffee on a table, for example. No wonder then that some scientists have regarded his work as stretching beyond the realm of physics. And not just scientists, Nagel's work is now also a routine part of what we discuss in our humanities division, in the university's Gray Center for Arts and Inquiry, for instance. Professor Sabyasachi Bhattacharya is a renowned physicist who works on dynamical aspects of disordered condensed matter systems. He is a fellow of the American Physical Society and of the National Academy of Science in India. Having had a long career in America, working as a senior scientist with Exxon and then with NEC Research Institute in Princeton, he moved back to India in 2002 to take up the directorship of the prestigious Tata Institute for Fundamental Research in Mumbai. He has since held the Acharya J.C. Bose University Professorship and the Sir C.V. Raman University Professorship with the Presidency University in Calcutta and the Ashoka University in Delhi, respectively. He is at present the director of the TCG Centers for Research and Education in Science and Technology and is based in Calcutta. Most importantly for our purpose, I should mention that Professor Bhattacharya was once upon a time a young postdoctoral fellow at the University of Chicago, working with a young Sidney Nagel when Nagel's work was at a very interesting turning point. So with this introduction, over to you, Shobho, and to the wondrous world of contemporary physics.
Thank you, Dipesh, for letting me curate this very interesting conversation. Thanks to the University of Chicago's India Center for organizing these dialogues, and I take the opportunity to thank Aditi and Suman at Delhi, and I especially like to thank Abhik Chanda, his colleagues Anitesh and Akash, who are behind the scenes. You don't get to see them, but they run all the strings that make this kind of program possible. So I begin with a very good morning here at Hyde Park. I also happen to be at Hyde Park at this time. And a very good evening to our audience in India and everywhere in between. For me, it's extraordinary pleasure, just as Dipesh mentioned, to be back in conversation with a person with whom I have conversed for more than last 4 decades. And I looked up. I joined University of Chicago in 1979, which was another era. And during my time in Chicago, there was a presidential election, which had Jimmy Carter, who was a physicist by training. He knew how to count. He conceded the election. Ronald Reagan became the president. India had 3 prime ministers during that period: Morarji Desai, Charan Singh, and Mrs. Gandhi, all results of elections and so on. And these were very, very interesting times. And particularly for me, because I got to work with Sid at a very, very interesting time of his career, which I now realize. And Sid will attest readily to this now in hindsight, that now I need to tell you why that was an interesting time. See, what we physicists typically do is that we do something during our PhD period and our postdoc period, and that stays with us very close to the surface for the rest of our career. Sid did something extremely unusual, which is the main subject of our discussion today. Sid abandoned his moorings in what he did for his earlier work, although he retained an interest in disordered systems, but he departed almost never to return again. And this is very, very unusual. And today what we are trying to do is to explore this departure that he has had in his career. And I would just like to start by saying that this departure, ask him, bring him into this conversation and ask him, then in hindsight, after all these years, does he think that this departure was an active decision? Was it happenstance? Was it accidental? Was it serendipity? Or was it some inner urgings that pushed him inevitably towards this direction? Whatever you want to say about that, Sid.
Okay. Well, thank you very much, Shobho. And I also would like to thank Dipesh and the Delhi Center and everyone who's worked behind the scenes to put this conversation between the two of us on the air. As you said, we've had this conversation or something like this over the past 40 years, many times. And so now I guess we're going live with this. So to go directly to answer your question, I've never been good at planning. And so the forces at work that have put me in different paths in physics were not planned in advance. I didn't have a view as to where I wanted to end up, but there were kind of forces at work in the sociology of the physics that led me along this path. And at each step for myself, I always thought that I was only making a very small excursion. But if you live long enough and you make small excursions, you get to go pretty far away from where you started. And so that's kind of how I feel what's happened to me. So if you ask kind of what is the area that I'm, how have I ended up here? I would say it's an attraction to certain types of physics that I've always liked to do. And so just to say that in some areas of physics, the questions are very well articulated. And the supreme effort of all physicists in those areas is to do tour de force experiments or tour de force theory to answer those questions. And there are winners and losers. I mean, there are the ones who reach it first, and those are the winners, and those who come up behind are losers in that endeavor. And it takes someone great to be the first. I mean, there's no doubt about it, and you know who's the first. But in the area of physics that I've somehow drifted into, it's the questions themselves that we're struggling to articulate. We don't know the questions ahead of time. And our efforts are to find out what are the good systems to exemplify this phenomena, and what are the right concepts to follow to find a universal behavior between the various systems that we choose. And so we're basically kind of like hunters going out to find out what is something interesting to look at. And the emphasis is not so much on winning or losing, but to find something that everyone else will want to study. And so this is kind of what what I like doing, what I really love about this area of the physics. But on top of that, so that's the sociological answer to your question in a way. But I also think that the questions that we deal with in this area of science, it's not just physics, it's kind of broader than that, are exceptionally deep. And so I think Deepesh mentioned this at the beginning, about order and disorder, but as physicists, we know very well how to deal with very ordered systems. And so there's a great mathematics and physics theory about how to deal with this. And, we kind of understand that. But if I look around me, we can't see this room because I've hidden all the disorder, but there's disorder everywhere. I mean, and not just at this macroscopic scale, but even at the microscopic scale. And so the question that I've always been fascinated with is, well, if you have disorder, what new phenomena does that bring with it? And so that's something that I've been excited about studying throughout my life. But another thing which is perhaps even more larger in scope is that, as physicists, we've understood something about equilibrium phenomena. And so, for example, if I gave you a small box of gas, I could bore you stiff with telling you all the properties of this box of gas because it's an equilibrium. We know how to treat this. And so this is a well-developed science. But, I look around me and, the atmosphere is certainly not an equilibrium. Things are very far from equilibrium. More than that, I would say, you look around you and you see, well, nothing is in equilibrium. That is, if I look at you, you're not in equilibrium. If you were in equilibrium, you'd be dead, right? And
right.
That would be a very unfortunate way of existing. I mean, so it's this idea of what, so all of biology is basically geared at keeping us from being in equilibrium. And so this is something that I find a very interesting area. And then I guess the third part to answer to your question is that the phenomena that I get to study in this area has a strong appeal to me. I mean, the phenomena are striking, they're surprising, and yet they're familiar. And so familiar indeed that we forget to realize how bizarre this phenomena really is. And so let me just give you an example of that. So I brought this tube, and so you can see it's a tube about a foot long and 30 centimeters long, and I filled it with sand up to a certain region. So you can see, I put my finger here to the top of the sand. I hope you can see that there. And so
yes, we can see it. Yeah.
This is things have a fixed density, but all I have to do is tap this a few times, and now you see that the sand has fallen to this height. So this is a large change in the height of this material just by tapping it a few times. This is what happens because you're not in equilibrium. I don't even know what the density of something is unless I know its complete history. And so this is a new type of phenomenon. Another striking phenomenon that I would like to show you, and so this is, let's hope this works, is I want to show you, I have here just a white plate. I'm going to put on this white plate a little bit of paint. And so you can see here that there's some paint on it, I hope. And now I'm just going to squeeze this between a transparent plate in front so we can see what happens. And this looks like it's the world's most boring experiment, right? That is, it just goes out in a nice circular disc. That's really dull. But look what happens if I just now pull this apart. if I can. And so what you see is that this thing has now a beautiful set of shapes have emerged. This pattern formation has just been in your face, and I want the whole world to see this. I mean, this is a demonstration that we developed so that we hope that a museum could take this for a science museum to bring kids in to show that they can make their own patterns like this, and they're really easy to make, and they're ubiquitous. They're all around us. So this is, what we see, without doing too much in the, we don't have to look too far. But what I just want to show you is, well, then we take this and we put this into the laboratory. And so here is how that experiment would be studied in the laboratory. So now we've done this in a much more controlled fashion. We have two plates that we're going to inject this liquid into. And so now there's a gap between those two plates, and this liquid is going to now spread out laterally. And so this is what happens. And so I'll play that again. And so you can see that you see these fingers forming this, and then the fingers form, and then on top of those fingers, other fingers form, and on top of those, more fingers form. That is, it's this thing forming. The same process seems to be happening over and over again at finer and finer scales as you go out. So I want to now relate that back to kind of patterns that we're familiar with. And so one of the ones that, I think we all see very often are these trees that I'm beginning to see now as winter starts to come here. We see that we have, the same kind of pattern, this fingering. Before, what I was talking about was what's called viscous fingering. Here, it's just tree patterns. And you see this in many different guises. But here, if you took a small little region of this photograph and blew it up, you wouldn't be able to really tell me, was that the small part or was that a bigger part of the tree? That is, the same shape occurs on different scales. All I have to do is blow this thing up. And so this is a symmetry of nature. And it's one that physicists like very much. It's called dilation symmetry, in the sense that if you dilate the image, as you make it bigger, you regain what you saw at the smaller scale. And so it repeats itself at all these different scales. So this is one aspect of what I find intriguing, and the ubiquity of these patterns, and how can we understand them, and can we look at them at a deeper and deeper level. Another area is just, well, how does a drop break apart? And maybe we'll talk about this a little bit more in a little bit, but
yes.
This is just an air bubble rising in water, so it's held down at the bottom, and it rises, and then it breaks apart, and you get to see this beautiful set of oscillations on that air bubble as it rises, and you see these beautiful shapes. And I find now this is going towards the just splendor of that object in front of us that I find intriguing, and I like to look at it. It's what better can I do with my life than to spend in the laboratory so I can watch movies like this over and over again all day long. Another example is this, where I'm taking two drops and I'm bringing them close to each other, and they suddenly touch, and then they coalesce into one bigger drop. And so here is that shape. And again, there's something really, this happened very quickly. It was very small, but you expand this up and slow it down so that our senses get to feel this, and it gives a sense of inner peace in this to me. That is, it's really something evolving in front of you in an indisputable way that immutable. This is what it's going to be like. And so these are,
Sid, can I just ask a question?
Please.
You are doing this with fast cameras.
Mm-hmm.
Will you tell us all what fast means compared to the cameras we are used to?
Okay, so the cameras that I was brought up with, we thought we were doing really fast camera speeds if we had a 125th of a second, 1/125. And that was kind of what our point and shoot cameras were 50 years ago. These cameras are now, I'm able to do these movies that I just showed you were done with video cameras, which could take 50,000 frames a second. And so that's the speed at which we're viewing this. And I'm viewing this with the region that I'm looking at is only maybe a centimeter on a side, and then you blow it up and you can see all these features appearing. And I should just point out that I've put the name at the bottom of these slides so that you can see who really were the students and postdocs who did the work on this.
So, just a side comment is that, this kind of points to the intriguing title of our conversation, shadows and ephemera. So the shadows are between light and darkness, and we have plenty of shadows in your pictures. And it's ephemeral because in our normal scale, this is not available to us. It is just expanding this ephemeral phenomena into a long scale by experimental techniques that you are able to see this extraordinary thing.
And in the first place, it goes to this other idea of, well, I guess Walter Benjamin called it the optical unconscious, that you couldn't see it, but the camera is able to bring this out for you. But the other thing about the title, Shadows and Ephemera, of course, harks back to Plato's cave, right? Is that these are the shadows that we see reflected on the wall in front of us, but there's a real form in the back of all of this, which is what the essence of what the nature is. And, in some sense, a picture of this drop at the instant of breaking apart, that the air bubble is a form of nature. That is, it's in Plato's words.
Okay. You want to show a few more pictures, or shall I go into the next question?
I'll show this one last one, just because we talked about this was, again, something so familiar to you that, or to all of us, is that it's upsetting that someone might actually think seriously that this is something to be studied. And this is just, if you take a drop of coffee and you leave it on the table, it forms a stain. And, we've seen stains for thousands, hundreds of thousands of times in our life. I don't know how many stains I've seen. And, it never occurred to me that there was something funny going on here until one day I woke up and I was drinking coffee, and of course I hadn't cleaned up my counter before. And I saw that the stains looked like these things I'm showing you here. But what's funny about this is that you start off and the drop is high in the center where most of the coffee is. And if I had thought about it, I would have said, oh, that's where most of the stain should be, in the center of this coffee. At the end of the drying process, when this thing has dried out, that's not where the stain is. If you look at any of these images that I show here, the stain is all around the edge of where that liquid was. And so this is something that, wow, this is a question to be asked. That is, we've all seen this, and, and no one ever stopped to say, hey, this is funny, this is strange. And it is. And that was something that fueled part of our work. And so maybe I could stop.
And how did you get these rotated things all in one direction?
Okay, so that just because I was trying to make a photograph of this, and I put down a very large coffee drop, and it was very dull. And so I just took a straw and made it come out in these sun-like pattern. And so that was just how it was drawn on the sheet. And at the end, you see that very nice patterns emerge, that all of the coffee basically went to the very far extremities of this, to the edges, as far as it possibly can go. And so the shape of this was how I drew it, but it's what the coffee did inside that makes this an interesting thing. And so, it's, I think the true definition of a nerd is that I can't not look at stains. I mean, I walk across the street and suddenly I see a stain on the sidewalk, and I have to bend down to take a look and see what it looks like. And that's, I think, bizarre behavior, but I find all of these stains have something very elegant and beautiful about them because of the way the shape interacts with the flowing fluid on the inside.
Okay, that's marvelous. So maybe what I would like to do, because as Dipesh has promised, that your work extends beyond what we normally call physics. So for their audience, maybe I'll give you a very quick historical background of how physics has evolved, at least in the last millennia, if you like. So there is something that we call classical physics, and the high priest of that is a name everybody knows, that's Newton. And with Newton came other people like Galileo and Copernicus, and then later we had, and they found something called gravity and laws of motion. Later there was Boltzmann, who told us about what temperature is, and Maxwell and Faraday, who told us about electricity, magnetism, and all of this physics up until the end of the 19th century is what we call the classical age of physics. And for the purpose, you could disagree with this definition, but I'll use this definition just to give you a context. And the next major paradigm shift, if you like, happened at the end of the 19th century, at the turn of the 20th century, and that's called quantum mechanics and relativity. And together they form what we call today the modern physics. So a part of today's discussion is to ask this question, that is modern physics the end point of physics? For a very long period of time, both Sid and I, and Sid will remember, that we grew up at a time when that was, and the search for the smallest indivisible part of nature, sort of, what can you reduce it to, was the central issue in physics. Elementary particles, we often call them fundamental particles, and that was the essence of modern physics and what came with it. About 70 years or 80 years ago from that, rumblings began to appear that this may not be the whole story of physics, that physics has more to do, and physics has more connections to make, as Sid was just pointing out, with equilibrium not being in equilibrium, being in systems that are complicated, systems that are macroscopic, but not so macroscopic that it's beyond human perception. And today we will try to explore, not decide by any means, but explore that in this kind of work, is there another kind of paradigm shift is going on? And is this paradigm shift have any connection with other aspects of human endeavor? So just like all of you, I think, Sid has shown me these pictures many times. I still remember the first time he showed me the coffee stain. But, it also reminds you of something else. It reminds you that this has extraordinary aesthetic quality of the phenomena that you observe. And it begins to beg the question that is this kind of new paradigm is beginning to go across the conventional barriers of physics, which is the subject of nerds, as it just pointed out, and get into the activities of people who are similarly creative but are never accused of being a nerd. The artists, for example, the photographers, the architects, and so on. So, maybe Sid will have some thought that while he was doing these experiments, and he might have more examples for us to see, where he's straddling and going over from conventional physics, that is modern, beyond modern physics. Postmodernism is a word that's heard often, and perhaps towards the end, Dipesh will tell us a little bit about what similarities he sees. But this is something that has been on Sid's mind and on my mind, and we have spent many, many hours discussing this business of the postmodern world and whether or not physics too has a postmodern version. And this is what, consciously or unconsciously, Sid's work is aiming towards. So I leave it to Sid, not that he needs to answer this question, but he needs to kind of talk to us about what these thoughts mean to him. Are they meaningful? Are there examples where he can illuminate this area of, this kind of thinking? So
okay.
up to you, Sid.
Well, that's a set of questions, and I'm not sure I know where to start with all of this. I'll try and share the screen again so that I can at least have something up here to show. There are various aspects to this. I think you and I have talked, but it was actually started when we had a conversation with Dipesh about, postmodernism in the world. And then I remember you and I looked at each other and said, hey, that's kind of what we do also in the lab. Maybe we'll talk about that a little bit later. But, I find this idea of, well, what is the place of science or physics or the kind of stuff that I do in the world? And so there's questions of where does it fit into culture? Where does it fit into answering scientific questions versus something else? And so I guess to maybe start the second aspect of this. So here is an image that I remember when we took this. It was we spent the day, and all night long working on this in order to get the lighting right, to get the shape right, to get it at just the right instant of time. And this is a drop breaking apart. And so it's to me, a very interesting physics question. That's what we started out to investigate. It's this question of how does a drop break apart? And so why is that an interesting question? Well, if you look at this picture and you say, well, just an instant before this, all that liquid was up at the top surface of this, the holder, and then gravity started to bring this down. And as it does, it stretches the liquid, leaving some at the top, some at the bottom. And there's a neck in between. And as the time goes on, this neck shrinks and shrinks and shrinks and shrinks until it has to go to zero radius. If it didn't go to zero radius, it would still be connected. So the very fact that this drop disconnects from the liquid above it means that that radius has shrunk to zero. And the one thing I can just tell everyone in the audience is that there's one thing we know from fluid mechanics, which is that the pressure between the inside and outside of a liquid is just equal to something called the surface tension, which you may be familiar with, divided by that radius. So if that radius goes to zero, that means the difference in pressure at that point is going to infinity. So we have an infinity diverging, something is blowing up right in the middle of our experiment. And we don't know how to treat that. I mean, mathematicians don't know how to treat that, and physicists don't know how to treat that, and yet nature seems to be able to do this just fine. It just, the drop falls and it breaks apart, and it doesn't seem to think about it, but we don't know how to think about it. And so that was part of what this this effort was. And so I'll just show you a couple more images of different fluids breaking apart. So this is a water drop on the left, the more familiar one. But I also put next to it a few equations that come from the papers that describe this. And you can see that the equations are, I guess, someone might find them beautiful. Not everyone has to find those beautiful, but there's an idea in them, and especially in that the top one that I drew there. And that's the essence of the idea that we were trying to get at in these pictures. And so what I want to say is that, look, I was a physicist. I was trying to understand what is the physics behind this. But then you see the splendor of this phenomenon. And I, for one, can't just let it go. I mean, it's a splendor happening in a somewhat different realm from those physics equations. And I want to know, well, how can I reunite these? I feel empty or incomplete if I haven't been able to put those two things together. And so this act of trying to make the image and make the image as best as I possibly can to really capture what I imperfectly can see as the essence of this object, the what gives me pleasure, that feeds me in a way that I don't want to neglect. And I think science alone is one thing, but the science plus the image is bigger, is a greater thing. And so that's what I have been at pains to try to make clear, that it's not irrelevant. It's not a different aspect of it. It's not just an illustration of it. It's something that goes alongside of it and helps make us, it's part of what makes us human, is to realize that both sides of these are important. And so at one point I was criticized for trying to make this into something beautiful, or I shouldn't use the word beauty because I'm not quite sure what beauty is, but to try make contact with this other aspect of this phenomenon. And because that's not what a physicist should do. I mean, I should just concentrate on the equations or solving the problem. And I disagree with that completely. That is, I think it's destructive to wall off part of what makes us human from any other part. And so I don't know if that kind of answers one part of your question, Shopo.
It certainly does. It certainly does. And this reminds me of something we read in books, that when Newton, our great Isaac Newton, wrote down his equations of motion and discovered gravity, there was a revolt in the artistic community, led by very, very eminent poets and others, who accused Newton of taking away mystery, or taking away a very unique part of human existence, imagination. That, oh, now there is no room for imagination, and he was subjected to a lot of ridicule. And lots of painters drew cartoons of things, saying that he took away the human element of art and of literature, of poetry, by encapsulating all of this in a few dry equations and a few observations and saying, well, the apple fell on my head by the same rule that the earth is going around the sun. So there was no wonder in it. And today what you are saying is kind of that same thing upside down. You were saying that, I'm going to do science, and what I'm discovering is a layer of beauty that you didn't know existed. And this beauty is beauty even in terms of people who are painters or architects or designers and so on. So it's curious that history repeats in this particular case in an inverse way. I just thought that was an interesting question. But I just, for the remainder of the discussions, I'd just like to, give you two sort of general direction of thought. The first one is something that's familiar to all of us. C.P. Snow's famous Reed lecture called Two Cultures. And teaching an undergraduate institution only recently, rather late in my life, I have begun to see that these two cultures have remained two cultures, that all of this work over the last hundreds of years have not brought us together as much as you would have liked to see. And institutions, by and large, museums that you alluded to, do not do justice to bringing this together. And that your pictures adorn the walls of the Chicago Center in Delhi, for those who have seen it, often do not know that these pictures were the results of scientific investigations. Knowing them perhaps would give them something more like what you have been discussing. So that's sort of, one point. And if you wish to say something about whether or not artists and scientists and architects, there is some commonality in how they work. We have nature. Nature cannot be violated. It's arbitrary. It decides whether we are right or wrong. So that's one kind of question. And the second kind of question that I want to come to, perhaps after you have discussed or given us your view on this, is back to something like words. Do words matter in science?
Okay.
And specifically, I want to go to a single word, which is fundamental. But maybe, and you can probably see where that question is leading to, but maybe you want to say something about the first part of commonality or dissimilarity or whatever.
Science is part of culture. And that's something that I find is somewhat missing in certain descriptions of it that I've come across. And so, this is a dream that I have, and it's like most dreams, probably unattainable, but and still something that I like to think about. And I always think of museums as a repository for culture. I mean, so this is where we go to find out what culture is like. And in particular, as I've been around longer, I tend to gravitate to those museums of contemporary art where they have retrospectives of some contemporary artist of what they're doing. And why do I gravitate to them? Well, it's because they show how some artist has looked at the world and has a vision that has made us look at it in a different way. And so I remember going to various retrospectives and say, wow, okay, so this is a new, the worldview that this artist seems to have, and either conceptually or in what the figures are, and it shows us something different about how to perceive the world. But I also think that science should be viewed in that same light. That is, some sciences or scientists, or perhaps branches of science that they helped establish, have also changed the way we think of the world. So for us, I mean, as physicists, we know some of these names, but I'll just say to everyone else that these are names that we all look up to greatly in the physics world. I mean, so De Gennes and Leo Kadanoff helped us look at the world in terms of scaling, and this idea of dilation symmetry that I talked about earlier. They championed that, and as in the image of the trees that I showed, this is somehow that they see the whole world as somehow emerging from a kind of that kind of symmetry from the small to the larger aspects. And so this is one worldview that has changed the way we think. I mean, Phil Anderson, who's another great physicist, made us aware of how interactions change the way that nature behaves in very fundamental ways. And what I dream of is somehow a curator, and it would take a curator of immense perception and knowledge and everything, but some curator putting on a show where in one room there's a retrospective of some artist's view of the world, and that changes the way we think about it. But in an adjacent room, there's a retrospective devoted to some scientist who has also changed the way we have looked at the world, and maybe in a similar fashion. I mean, I can see there are certain cases where I say, oh, well, these two ideas somehow are similar in a way, but they're phrased in different ways, but they're both changing how we want to see the world. And so it would take an incredible curator to do this, but wow, that would be such a great show if we could put that on. And so that was one idea of how these things are both part of the same culture. You also talked about science as, being perhaps forbidding because a scientist must conform to the strict set of constraints as the laws of nature. That's kind of what you were saying. But, and so then you would say, well, a derivation is either right or wrong, and there's nothing in between. I mean, there's truth and there's non-truth, and that's it. So this seems to be unforgiving. But what I want to kind of point out is that there is that every art seems to have a complete set of constraints also. And the one that I love being here in Chicago, where we have great architecture all around us, is architecture is a great place to see this, that an architect must, on the one hand, build buildings that conform to all the laws of nature, but they have the constraints. They have wind coming in, they have earthquakes, they have floods. They have all of these things. They have to worry about how people interact, the social parts of this. All of that has to go into making a building that's really a sublime building, and that's no less full of constraints than what we have to do in physics. It's just that we don't somehow worry about those to the same extent. And so the one last thing I guess I just want to end with that part of the question for this is that we have, making these commonalities between humanities and the sciences. And I have one example that I like here, which is the issue of a liquid drop that is falling and then is going to the table and splash. And so it should show up in a second on the screen, I hope. But what I want to point out about this, okay, there it is, about this drop splashing. This is just a liquid of it's a small little drop, a few millimeters in diameter, and as it falls, it's going to hit that plate below it, and it's going to splash. And so we'll see what that looks like. And it's a phenomena which is elegant in itself, and I appreciate looking at that because I think that's something that is fun to watch over and over again. But the issue that we asked was, well, what makes it splash? And when we asked that, we got a completely surprising answer. And it's so surprising that it borders on what I would think of as nature. As in humanities, you would have, there's the idea that there's a joke. And this one is a joke to me. So it's totally true, but So here is this drop splashing. And this is just ordinary, just doing it on a tabletop. It's nothing unique about that. But what we wanted to know was, well, could we make a really big splash, an enormous splash, by taking away the air? After all, the air is, these drops have to flow through the air, and so they're going to be slowed down by this. So if we took the air away, we would get an enormous splash that covers the whole, much bigger than the one that we just saw. And so what I want to show here is, after we did that, looking for this enormous splash, this is what we saw. So the same drop comes down, and it just spreads. And when we saw that in the lab, it was like a cosmic joke. I mean, we just started laughing hysterically at this. I mean, this was not supposed to happen. It was exactly the opposite of what we expected, just like a joke. As a joke comes in and twists you all around, and this is something that twisted us all around. And so this is an example of, again, how we have this common connection between things that we see in the laboratory and things that you would read about in humanities, issues in the humanities. And so maybe that's the end for that question. So that
okay, yeah, I have seen this probably not as many times as you have, but I have seen it many times, and every time I see, I find it to be amazing that this happens. So what I'd like to do now, in the interest of time, is ask you this question, because I know the answer. Is not all things that you have shown us are things that you fully understand, and there are things that are still on the way of being understood. And could you, at least for now, leave the science part with something that you do not quite understand, but in the process you have found something quite extraordinary, something visual to leave our audience with? And after you have done that, then I'd like to bring in Dipesh into the conversation, because we are now then going to talk about what is fundamental and what is postmodern. And it would be good to have him in that conversation.
Just to very quickly end up this subject of the drop splashing, which I just told you about. I mean, we've been working on that. We found this effect, a decade ago, and we've worked hard on this for a long time. And it isn't as if we can understand the answer yet. It's not a fully solved problem. But to give you some idea of how, as a physicist, we try to look at the problem. So what kind of tools do we have again? So we used photography again. But what we're now trying to do is find out, okay, so the air mattered. That is, if I take the air away, the splash completely disappears. So I want to see, what is the air doing during a splash? And so this is a different kind of photography. It's called Schlieren optics, for those of you who know. But what it does is it tries to bring out the contrast in the fluid around, the air around this drop. And so what you see here is this black drop at the top of the screen, and that's going to fall and hit that black platform below. Those are the two things. Those are the uninteresting parts of this movie. What I want you to see is what's happening when I play this movie to the gray scale around this drop. And so here is I'm going to stop it just so you get the idea of what you're supposed to look at. So here it goes. Okay, so I stopped it there. What you see is that as the drop falls, you see the wake of the drop. That is, it's where it's dark right where it's fallen, because it's changed the index of refraction in that little area by a little bit, and we were able to magnify that with this photography. And so that's what I want everyone to look at, is the gray area surrounding the drop, not the drop itself. Okay, so let me now just play the full movie, and so you can see where the air and what the air is doing in this case. So I find that very comforting in a way to know that despite all of the problems that dripping drops fall and make a mess, and the bathroom sink that keeps dripping has a leak in it, and so I keep hearing the drip, keeping me up at night. But there is something about what's happening every time that drop falls and hits the substrate below it that is just like this. And I find that it's something that enhances the way I think of nature. And whether I understand it or not, it's something that we've discovered in the lab, that this is what happens. And I find it gives me great comfort. And we don't understand it.
Great. This is an extraordinary thing. So I think our audience, every time they hear a leaky faucet or hear a drop, should imagine that, air around that is going through these rolls, these vortices. And perhaps this will not fix your leak, but will give you some comfort that you know how beautiful things are happening, unbeknownst to you or unbeknownst to those who have not seen this demonstration. Something extraordinary that's happening. So what I'd like to do is, when we discuss the matter of fundamental, I thought that it would be a good idea to have Dipesh come into this conversation. And so what I'd like to raise is this question, is that in science, we are concerned mostly about content. And we don't worry so much about exact words that we use, but words other than scientific words, nerdy words, equations, and stuff like that. But the word that has bothered me for a while, and lately more than ever, is the word fundamental. At the institution I worked for 20 years had fundamental in its name. And fundamental used to mean something good. Fundamental meant something basic, something essential, something at the core, something central. And one was proud to do fundamental work. On the other hand, as we all know, painfully, that the word fundamental also connects in other areas of human society to the word fundamentalism. And as soon as I tell you fundamentalism, there are other images that come to your mind. Instead of essential, core, it sort of means narrow, fanatical perhaps, intolerant perhaps, thinking of things only in a narrow way. It's kind of not what we had in mind when we were doing fundamental science. So, what I'm seeing in what you are showing is something I wouldn't call fundamental, but I'd like to say, as you and I and Dipesh have often discussed, is I'd call it perhaps universal. That you were looking at patterns that span wide range of phenomena, which are held together by some similar concept. So rather than putting things away, it puts things together. So it's much more of a unifying idea. And I thought it would be, interesting to hear, this attempt that we are making in a public discourse, public dialogue, of asking whether or not beyond the modern, is there another kind of paradigm shift that is on, which is different from the previous ones that science had known, and how that connects to the humanities and social sciences. So now, instead of a dialogue, it's a trialogue. And Dipesh, you get to start this off.
Yeah, I think I'll let. Yeah, I'm unmuted now. First of all, I want to say this has been a wonderful conversation. Great to be there. And Sid, it confirms me in my impression that I've always had about your work, is that your work, one could say in an expanded sense of what the humanities are, is part of the humanities. I mean, I would love to claim you. I mean, you do maths that we don't understand. And maybe somebody would say maths is physics, but in the end, I think, and I'll explain a little bit, you are actually looking at your scientific questions as part of what in the humanities we would call the human condition. And that comes through. So I'll just quickly talk a little bit about that and come back to the question of fundamentals that Shobo raised. So I was very struck by the way another word and corresponding word were littered in your language, and Shobo didn't pick up on it, so I picked up on it. One was beauty, it's beautiful, and one was elegant. And when you had the equation by the side of the drop breaking off, you actually said, some people may find the equation elegant, but the drop is beautiful. And see, and the fact that the drop is beautiful, or the point that the drop is beautiful, would probably be agreed to by most humans I know, even if they didn't understand the elegance of the equation. So it seems to me that in some sense, that response that the drop is beautiful is more, shall I say in Shobo's sense, more universal, if not fundamental, than the response that the equations are also beautiful or elegant. Because the equation, that to call the equations beautiful or elegant is in a way to conceptually transfer something we perceptually see as symmetry, elegance, balance, onto some numbers or algebraic symbols, right? And see symmetry, see economy, all of those things, and then say this equation, this solution is elegant. And you know, this point was actually made philosophically by Husserl, the great philosopher of phenomenology, when he was talking about the question of the Earth moving around the sun. And he said, you know, there are two Earths. There is one Earth for the astronomers, which the astronomers or planets or the sun, the astronomer looks at, let's say through telescope, you know, early modern whatever. And there's another Earth that the astronomer as a person inhabits. So while we know from astronomical calculations and observations that this other Earth and other planets are moving, and sometimes moving at quite phenomenal speed, but when the astronomer takes the path he takes every day from his home to the observatory, that Earth for him doesn't move. So he doesn't wake up one morning and finds the path has gone somewhere else. And therefore he was making the point that humans are grounded in their perceptions of the world, while cognitively we can see aspects of the world that we cannot perceive. So we can't sort of feel the radio, you know, magnetic waves, electromagnetic waves around us, or you know, you might not see ultraviolet rays or infrared, whatever. We know that they exist. We know that they have impact on us. If the ozone layer is damaged, these rays have an impact on us, but we don't see them. And the phenomenologists were arguing, but you see, you can develop knowledge of that sort. But the grounding of human existence is in a world where even before you have explained to yourself what beauty is, you exclaim it's beautiful. You know, in the way that a philosopher of God once said that that being human is to be able to say, "Oh my God," without having to think about whether you believe in God or not. Right? It's able to address that. So in that sense, I thought your physics is very much, it comes out of, and I think you explained it beautifully when you, and I use the word beautifully, when you talked about your visits to museums, is that it comes out of your interest in explaining what we see, sometimes with our plain eyes, and sometimes when the capacity of eyes for our eyes have been extended by the use of particular kind of camera, by the use of microscope. You know, so there are so in some ways this distinction we know and we make between the world we perceive and the world we cannot perceive. Black holes we don't perceive, right? But in the end, Husserl would argue that our very language for speaking about all of those things we don't perceive is grounded in the world we actually perceive, however limiting our perceptions might be. Now, the way it connects up with Shrubbo's discussion of fundamentals is that what happened in the 19th century as social sciences emerged, like sociology, anthropology, and as these things took on some kind of analytical stance on the world, they modeled themselves as what they saw as the huge explanatory power of physics coming out of what Shrubbo is calling classical physics. Physics' capacity to reduce many phenomena to some fundamental particles, laws, connection like that. So this what we might call reductive, but what they saw as an economical capacity of physics is something most social sciences copied, and probably was copied most consciously by economics. And you get economists writing in the 1920s saying economics wants to be the physics of society. But the assumption was that what people perceive in everyday life doesn't tell them about what's really real about their lives. It doesn't tell them why they're suffering, why they're happy. So somebody would come along and have to say, you know, you think you're suffering because your boss behaved badly with you yesterday, but you're actually suffering because you and your boss belong to a system called capitalism, which you can't perceive, but which is the really real thing behind your back. So that's why many of these explanatory devices in the social sciences thought that they had the function and the duty of demystifying the world for people. So that was modern social science. So society was imagined like having a surface and a depth.
Right.
Really deep things happened in the depth of society. We lived on the surface. So everyday perceptual phenomena of, you know, I'm unhappy, I'm falling in love, I've just written a poem, was all superficial or surface related. But they were all being determined by this really real level of reality, which was to do with capitalism, or Max Weber might say it's really the Protestant ethic that makes for capitalism. So everybody had a key, or Freud would say it's really sexuality, you know, anything that happens goes back. So these are the modern social sciences, and their job was to demystify. And a lot of so-called postmodernism was a rebellion against the tendency to demystify and to say, look, the really real things don't always happen behind my back. I'm not always being deceived by the reality I see and I inhabit, right? And so in many respects, that's where the move has been. I think so there is a kind of similarity between, and it's not accidental, I think, between the sort of rebellion that your work embodies, where you are saying, you know, I acknowledge that there's physics in the equations, and there everybody is agreed. But there is something else in addition to the elegance of the equations that is also beautiful. Where I said you use the word beautiful before you have to explain it, because most people would agree with you that it's beautiful, and that's given to our perceptual mechanism, the kind of organisms we are. We already have that hardwired into us to actually see beauty in sunset, to see beauty in somebody's face, to see beauty in that drop, in that, and so philosophically speaking, to me, to place you, I would say, and it goes back to Shobo's point about the two cultures, that your rebellion against what Shobo described as the fundamentalist approach of physics, but going towards to more universal. So one could say the perceptual mechanisms we have are universal. Whether you're yellow, brown, or white, or black, it doesn't matter. I mean, our brain was formed long before we got the skin colors differentiated. You know, so our perceptual mechanisms are much older than the history of recent cultural differences or physiognomical differences. And for that reason, I like Shobo's description of the arc of movement as from fundamental or a fundamentalist view of the world to what he calls more universalist. And the difference to me is that with fundamentalism goes a depth model, at least of society, where I'm saying you are living on the surface, and what you experience on the surface has to be discounted in favor of some analytical gaze that sees into the depth of society and can tell you what's really going on and demystify your experiences. Whereas what your equations are doing, your equations are actually helping us to understand the formal properties of the forms we already see as beautiful. Right? So just to come back to India, since a lot of our listeners in India, when you said that where the radius of the drop becomes 0, and even as the drop breaks off from a leaky tap, for every drop that breaks off, there's a moment when there's a peculiar formation which you can only understand with the help of the conception of infinity. It's a beautiful poetic point as well, which actually the Bengali poet Tagore always used to say, that life is about finding the infinite in the finite. Right? There's a Shimar Majhe Oshim, as they would say in Bengal. In other words, the unlimited in the limited. Right? And again, it sort of reminds me how poetic your work is. And I'm not at all surprised that my colleagues in the humanities love your work, even when they don't understand the mathematics of it. And I think it's a great contribution to the question of two cultures that Shobo raised again. Because the cultures have always, in spite of the, I mean, there's been more, I mean, first of all, you get prejudiced individuals in all fields. And secondly, lately, I think in the last few decades, there's been a lot of prejudice that's grown in the humanities against sciences, partly coming out of even science studies, and that has to do with the way that big corporations and the military industrial complexes and governments have used science, created big item tickets in science, and given scientists a kind of power which is far out of proportion to the explanatory power of science. Because when science is what you do, you are very happy to say, this is what I don't understand. Yes. Or as Shobo was saying, the things you say, I don't fully understand, but I can see that this is beautiful. And I think that's where the prejudice against science comes from. It's a social prejudice. It's actually a social prejudice against the kind of social power that science has attracted to itself, or economics has attracted to itself, right? There's big money sometimes in the projects and consultancies and things. But on the other hand, you take us back to the spirit of science. And the spirit of science is not all that different. The training is different, but it's not all that different from the spirit of the humanities. when both are at its best or at its most profound. And I think I loved the transitional story that Chobo was trying to tell through the conversation, moving from fundamentals to universals. So this was a wonderful, wonderful discussion. Thank you both very, very much. Yeah.
Thank you.
Yeah, I think we may have some questions if we do, but there were a lot of appreciative comments that ran right through. I know that.
Okay.
Obik, you might. Okay, now there you get a question that I meant to ask you. Can you see the question?
Yeah, I'm reading. I'm trying. I'm a little small on my screen.
Do you want me to read it out?
Yeah, maybe that'd be good.
Okay, so it's Aritra Shom asking, your father, Ernest Nagel, was a major figure in the field of science and philosophy. How do you see your own world, your world of philosophy, and how does physics collaborate with that world?
Well, talking about my father, that's
that's another day.
Yeah, it's a hard thing. Look, maybe since you brought up the philosophy, Deepesh, and there's questions about that, I can say a few things. I mean, I find what you just said about Husserl very interesting, and what I see in a way is that you're trying to make a dichotomy as much as possible. I mean, there's this and there's this, and and of course that helps see what the camps are. But even in physics, you put these caps on, but it's always this middle ground.
Right.
And so what I would see for myself is that I'm trying to say, oh, let's remember there's that middle ground.
Right.
You know, that yes, there is this thing between the two.
Right.
And the object that you said about the beauty and then the equations, and again making that dichotomy, and I don't know if this is possible, and I can't be in that realm, but I hope that someone who goes to the Delhi Center and sees the photographs,
right,
if they do, and sees this thing, and let's say they are struck by it. I don't. I hope, but
that's, are. Well, I can tell you
that was the intent.
Okay. I can tell you that they are.
But what I would like them to have it, the fact that if they know that was taken by a physicist in the doing the research,
right?
Does that enhance the experience a little bit?
It does.
That's what I want to have. Is that yes? It helps us see that there are many ways of looking at this, and they're not incompatible, but that they are, as a physicist, okay, we did the equations and so forth, or I didn't do them, my colleagues did the equation, but I find that I get a better feeling about the science we did because, there's this image that captures something else, and I hope that that's true on the other side as well. So now this is not particularly asking about my world of philosophies, but maybe it's something I learned from my father. I'm not sure. He probably would not agree I learned anything from him. This is, but that's the job of a son, I think.
It's a fatherly complaint everywhere.
But is that that pushing things to the extremes is maybe helps at the outset to make it clear that there is this two parts of this, but that real life is actually some place where they meld in between.
Sure.
And so I don't know if that helps answer the question about that. But that is something that I kind of like. The other part that I certainly took from him was the idea that there are these fundamental laws that we heard Shobo talk about, which is but then there are these laws that came after that, and so is thermodynamics a lesser law than the laws of mechanics? And yes, maybe they rely on that, but the fact is that something new came out of the fact that we have thermodynamics, many particles interacting. There's this thing called temperature, and that temperature does not appear in any law that Newton wrote.
Sure.
And so this is a new thing. So that's something that I would have said is another aspect of this, that you go in both directions and find your new gods, either to the fundamental or to the emergent. And that.
And there's another question, Sid, from Sanjeev C, and it says, do you think human relationships mimic the dynamics of coalescence?
Wow, that's interesting. Well, yes, so I do think I can read into just about any physical phenomenon that we've seen something where nature comes in. I mean, so in some of the things we didn't get a chance to talk about it, I see, the role of memory in things, and that makes me think, oh, in some drops, it's nature versus nurture. I mean, it's how did things start versus what is independent of what the history was. In the case of coalescence, if I look, to be honest, I never thought of that question before, so I'm just going to wing it here. Is that so? What is the first thing that comes to mind for me is that if I take those two things coming together, and I saw that spreading out into that, as they merged, and you saw the movie just before that, which was the drop coming apart. So those two things are really, you would say, oh, that there should just be time reversal of one another, but they're not. And so maybe that's, if two people come together in love, and that's coalescence, but when they break apart and split apart, that's a very different set of feelings that come with it. And so that's the best I can do for saying how there's a connection between the two. I hope that's acceptable. It's
Okay, I think, yeah. And the second question is a variation of the first one, more or less, and I think you've already answered it. Bobik, I mean, we are running a little over time, but Bobik, are there other questions, or? It doesn't look like we have other questions. So look, and we're already a bit over time. So since I'm on screen, I have the privilege and the opportunity to thank you both very warmly and very gratefully, and for what you've done. I think this was a wonderful conversation, and I hope people who tuned in enjoyed it and were enriched by the experience as much as I was. Thank you very much.
And thank you, Deepesh and Shobo and everyone at the Delhi Center for allowing me to say our thoughts. So thank you very much.
Okay.
Thank you.
Thank you. So.